I've previously discussed gravitational lenses and speculated on what some of these images might be showing us. Halton Arp was actually part of the first discovery of the Einstein Cross images, often attributed to gravitational lenses, but he had very different ideas about what had created them. Let's explore how Arp became involved in gravitational lenses and how he saw these fitting in with the rest of his data. Prior to the 1950s, it had been demonstrated that light rays could be bent in the vicinity of strong gravitational fields. One such example was the famous movement of stars during the solar eclipse. Fritz Zwicky started looking for an extragalactic object which might be directly behind another, and thus have its outer light rays bent inwards by the gravitational field in the foreground object, so that it formed a ring or a halo. Initially, some ring galaxies were identified, but these all seem to be physical rings around the galaxy and not magnified background objects. The more common situation would be when the object was not exactly centered and the gravitational ring collapsed into a one-sided arc, but here too the search turned up nothing, so the subject lay dormant for another 10 to 20 years. In the 1960s and 70s, Halton Arp started finding high-density quasars concentrated around nearby low redshift galaxies. His findings were rejected based on the fact that the quasars could not be associated with the galaxies. It was when the theoretician named Claude Canizares got the idea that these associations might be background quasars magnified in brightness by the gravitational lensing effect of the foreground galaxy. Now Arp's observations were hailed as important, and many more examples were identified. Initially, gravitational lensing was the answer to these images, but when this did not work, it was once more rejected, but then microlensing came to the rescue. This allowed for the bending of the light by smaller objects such as stars or planets within the galaxy. The problem was that this now required a steep increase of the quasar numbers with fainter apparent magnitudes. Arp pointed out that this does not happen, and instead the number seems to flatten out. He predicted that if quasars were ejected from active galaxies, the distribution would match the distribution of these galaxies. And this is exactly what we find. Here we see the distribution of luminous spiral galaxies like M31 and M81 increases with apparent magnitude. The lines show how the various quasar surveys increase with apparent magnitude for quasars between z equals 0.5 and 1. The adjustment in apparent magnitude required to make this fit is very significant. For quasars between redshifts of 0.5 and 1, the displacement is 10 magnitudes, and this means that quasars of the order of 19th apparent magnitude must be found around dominant galaxies of 9th apparent magnitude, and this is exactly what he had found. For quasars between z equals 1 and 1.5, this fit continues, but now the shift becomes 11 magnitudes. This once more supports the idea that quasars become less luminous as they approach a redshift of z near 2.0. If we continued this extrapolation, then for these quasars we would require a 13 magnitude difference in associated galaxies, and this would make the 18th to 20th magnitude z equals 2 quasars generally visible in association with only the nearest galaxies like M31, the Sculptor group, and M81. Some of this evidence we have already covered in the first 3 parts. Now we can perform the same analysis of quasars with Seyfert galaxies, and once more we find the same association. This may well be the only reliable method for measuring extragalactic distances if redshifts are not due to velocities. For example, at the moment no one has the faintest idea where the mysterious gamma-ray bursters are located, but their number counts have a characteristic break resembling the break in the number counts from z equals 1 objects, and this means that they are probably distributed in space like the active z equals 1 quasars that we have seen throughout the Virgo cluster. Now, the most celebrated cause of a galaxy supposedly splitting the image of a background quasar into separate images is G2237 plus 0305, and this is what they call an Einstein Cross. When it was first discovered, it caused a panic, as it was essentially a high redshift quasar in the nucleus of a low redshift galaxy, and they had to invoke gravitational lensing to make this problem go away. Subsequent high-resolution observations showed 4 quasars of z equals 1.7 in the form of a cross centered approximately on a 14th magnitude galaxy of z equals 0.4. Since the 4 quasars were all within 1 arc-second of the galaxy nucleus, they could not invoke the accidental clause that they had all too often used in the past. When Arp examined the images, he clearly identified a luminous bridge between the quasar and the host galaxy. Examining the ultraviolet images, which included the Lyman alpha line, which is associated with the strongest emission line of one of the elements in the quasars, shows a clear connection between the quasar on the right and the host galaxy. And this should not be visible like this if it was due to gravitational lensing. To add to this, they later conducted an analysis of the spectrograph of the region between the top and bottom quasars and registered a broad Lyman alpha emission in each of the quasars. What they also discovered was a narrow Lyman alpha line in between the two. Here there is evidence of a low-density gas cloud at the same redshift as the quasars between the top and bottom quasars, which is precisely where the galaxy was. The evidence was obviously simply ignored and forgotten about. They continued to find more supposed crosses and used this as evidence that it was due to this amazing lensing effect. The absurdity of these papers got worse and worse, requiring even larger masses and sizes for the galaxies to create the required lensing effect. None of the images matched the theoretical image they supported. High redshift arcs are supposed to be highly distant background galaxies lensed by the gravitational field of the cluster and drawn out into thin conspicuous arcs. If these are true, then how is it possible to have a lensed object at the same redshift appear both as point sources and as arcs? They simply cannot have it both ways. Halton Arp was suspicious of the first observations of these arcs as lensed effects because he felt that high redshift objects were generally not so distant, and also because the galaxy clusters had much smaller masses than conventional estimates due to the redshift dispersion of their members. If we examine the arc near the Abell galaxy cluster, we will see some striking properties. A370 has a redshift of z equals 0.375. If we examine the redshift apparent magnitude diagram for the Abell cluster, we find it has an excess of 30,000 km per second. Peculiar motions of this order of magnitude are simply not contemplated for the conventional Hubble flow. Moreover, A370 is only about 1.7 degrees away from the large active Seyfert NGC 1068. Another example is MS0440 plus 02. Here the arcs look nothing like an elongated background galaxy. They look more like an ejected shell. We also find a Seyfert galaxy only 22 arc minutes away with essentially the same redshift. A casual inspection shows these active clusters lie strikingly close on the sky to low redshift and active galaxies than should be by chance. Radial gravitational arcs take this concept even further. Here the arcs point back to the center of the cluster rather than tangentially to it. MS213723 shows a supposed radial arc emerging from the center galaxy and aimed directly at the middle of a tangential arc. Now you might find some of this image familiar. We have indeed seen something similar to this before, when we examined NGC 1097. Here we saw an outward jet from a galaxy end at a right angle, and we also saw something similar in NGC 4651. So would it at all be surprising to find a quasar further out along from this central jet? And this is exactly what we find. When the X-ray cluster RxJ 1347.5-1145 was observed, 2 small arcs were discovered that seemed to center around it. These arcs seemed to be very short and aligned perfectly with the central galaxy. If this was due to lensing, then why are the arcs so small? And why is the interruption in the image so similar on both sides and so perfectly symmetrical? Could this be another example of a double quasar ejection that we have seen before? What would happen to this ejected material if it met some sort of boundary or resistance similar to the example of the jets that we have seen? Could this elongate the quasar? The galaxy at the center is a highly active galaxy emitting high amounts of X-rays similar to the ones we discussed in the last episode. This is exactly what we would expect to find if the galaxies ejected material, which in turn forms newer galaxies. Arp spent a long time cataloguing peculiar galaxies, and it is in these galaxies that we can find uncanny similarity to these so-called lensed images. If we start by examining the Hercules cluster, then we see many examples of disturbed and active galaxies. In this image, we can see one of these galaxies which seems to have a jet emerging from it. There is no doubt that this jet belongs to this galaxy, as the knots in the jets have more or less the same redshift as the galaxy. Here we once more see the formation of an arc at the end of this jet. To the south, close to the galaxy, is another arc that is much fainter but appears to stretch back towards the one above it. Here is another example of arcs forming around a galaxy with a jet forming on the other side. These arcs almost appear like ripples on the surface of water. Here is another example of this with very clear arcs and jets in the galaxy. Mainstream attempts to explain this as a galaxy merger, but if this were the case, then we would expect to see one spiral in on the other, not static concentric rings. The jets also indicate the explosive nature of the nucleus of this galaxy. The remaining question is whether ejected arcs can be composed of material which is of considerable higher redshift than the ejected galaxy. We know that these galaxies eject material in cones of various apparent opening angles. In NGC 7252, we see a striking example of this. Here we clearly see the material being ejected in a series of arcs. These arcs are getting thinner as they move outwards. If the same process of intrinsic redshift applies to this material as it does for the quasars, then these active galaxies might well be ejecting arcs of material that have a much higher redshift compared to the surrounding galaxies, making them appear as a lensed artifact. As always, be brave, be curious, the truth is waiting for us. Until next time.